Good day, my name is Martin Schiffner. I'm a PhD student at the Chair of Medical Engineering of Ruhr University Bochum, and in this presentation I would like to introduce the frequency-dependent f-number, which increases both the contrast and the spatial resolution in fast pulse echo ultrasound imaging. At the beginning, I would like to motivate the usage of an f-number and review two different methods for its selection. I will then propose a novel method for the computation of the f-number, which is based on the first-order grating lobes, and present a simple implementation. Subsequently, I will provide the results of three different experiments to validate this implementation. In the end, I will summarize the most important findings. The f-number is an important parameter in all image formation methods, using the delay and sum algorithm, such as coherent plane wave compounding or synthetic aperture imaging. The f-number significantly reduces image artifacts, as is shown here for a single plane wave. The neglect of the f-number, or equivalently, the usage of the full aperture, results in coherent image artifacts close to the array. The introduction of a fixed f-number, or equivalently the usage of a dynamic aperture, eliminates these artifacts. At the same time, however, such an f-number reduces the lateral resolution. The f-number for a uniform linear array equals the quotient of the focal length and the width of the receive subaperture. Two different methods have been proposed in the literature to select the f-number. The first method is based on the directivity of the array elements. An element of finite width W exhibits a directivity which is proportional to a sinc function. This directivity attenuates the recorded signals, which originate from the focal point and travel to a specific element. The remaining noise then causes image artifacts. A gap in this method, however, is that noise usually does not cause coherent image artifacts. A second method attributes these image artifacts to the undersampling of the array. The width of the aperture controls the grating lobes, and the f-number limits the grating lobe to main lobe ratio. The authors, however, use the paraxial Fresnel approximation, which is typically invalid. Although both methods yield similar f-numbers, which typically range from 1 to 2, they are mutually contradictory. Wide array elements, according to the first method, require large f-numbers or small receive subapertures because of their directivity. According to the second method, however, wide array elements suppress the grating lobes and permit wide receive subapertures or small f-numbers. Furthermore, the results of both methods depend strongly on the frequency. The research questions thus are: how does one select the f-number, and is it beneficial to account for the strong frequency dependence? To investigate these questions, we consider the receive beam properties. A receive beam consists of the main lobe and the grating lobe. This is shown here for a focal length of 30 wavelengths and an element pitch of 1 wavelength. To illustrate the field in the focal plane, we illustrate the profile. As the width of the receive subaperture increases, the width of the main lobe increases, and the width of the grating lobe increases too, because the grating lobe is simply a replica of the main lobe. In the focal plane, the main lobe becomes narrower and the grating lobes increase in amplitude. A further increase in the width of the receive subaperture then causes an overlap of the main lobe and the grating lobe. In the focal plane, again, the grating lobes increase in amplitude and the main lobe becomes smaller. The grating lobe to main lobe ratio thus increases in the focal plane. In the far field, the grating lobes move towards the main lobe and become wider. The proposed F number considers the angular spectrum of the focused receive subaperture and exploits the far field properties. The angular half-width of the main lobe is given by this expression, which depends on the F number. According to the sampling theorem, the angular distance of the first-order grating lobe equals this expression, where the first term is proportional to the sampling frequency. The main idea is to enforce a minimum angular distance to the first-order grating lobe. This can be accomplished by rearranging this term for the F number and inserting a lower bound on the angular distance. This is a closed-form expression for the F number, which only depends on the element pitch to wavelength ratio. To test this F number, we developed a Fourier-Domain beamforming algorithm. The inputs are a grid of image voxels and a set of RF signals. As a first step, we compute the Fourier transform of the RF signals, which results in a set of phasors in a limited bandwidth. This computation only has to be performed a single time. We then select a specific voxel and compute the associated apodization weights. These apodization weights are complex valued and include the delays. As before, these apodization weights only have to be computed in a limited bandwidth and account for the F number. These apodization weights are multiplied with the phasors to yield the weighted phasors. A lateral summation of these phasors then results in the Fourier transform of the focused signal that originates from this specific voxel. An inverse Fourier transform then yields the focused RF signals in the time domain. We extract a specific sample of the signal and assign the sample to the voxel. The last two steps can be combined into a single step by simply summing the weighted phasors over 2 dimensions. To test this algorithm, we conducted 3 different experiments using a Sonics Touch research system with a sampling rate of 40 MHz and a linear transducer array with 128 elements and a center frequency of 4 MHz. The excitation voltage was a single cycle at 4 MHz, and we emitted 11 steered plane waves in an angular range from -20 degrees to 20 degrees in steps of 4 degrees. The objects were a wire phantom, a multi-tissue phantom, and the common carotid artery of a healthy male volunteer. The F numbers we investigated were the smallest constant F number that removed all visible image artifacts, and this F number ranged from 3 to 1.5. We furthermore investigated the frequency-dependent F numbers, specifically 2 directivity-derived F numbers and the proposed F number. The wire phantom required a constant F number of 3 to eliminate all visible image artifacts in the vicinity of the transducer array. This relatively large F number, however, increased the width of the wire targets significantly and thus reduced the lateral resolution. All frequency-dependent F numbers approximately maintained the lateral resolution of the full aperture, but only the proposed F number, with a grating lobe limit of 40 degrees, was able to eliminate the image artifacts. To investigate the effect of the coherent compounding, we computed the axial widths, the lateral widths, and the volumes of the wire targets for 1, 3, and 11 steering angles. Shown here are median values and the interquartile ranges. The frequency-dependent F numbers achieved similar axial widths, similar lateral widths, and similar volumes as the full aperture. They outperformed the constant F number of 3. This outperformance was most pronounced for a single steering angle. The multi-tissue phantom required a constant f-number of 1.5 to eliminate all visible image artifacts in the vicinity of the array. Again, this f-number increased the lateral widths of the wire targets and reduced the lateral resolution. The frequency-dependent f-numbers approximately maintained the lateral resolution, but only one directivity-derived f-number and the proposed f-number were able to eliminate the image artifacts. To investigate the effect of the coherent compounding, we computed the axial widths, the lateral widths of the wire targets, and the contrast, specifically the generalized contrast-to-noise ratio of the anechoic regions. Again, we show median values and the interquartile ranges. Although all f-numbers achieved similar axial widths, the frequency-dependent f-numbers significantly reduced the lateral widths of the wire targets relative to the constant f-number of 1.5. The lateral widths were comparable to the full aperture. Furthermore, the frequency-dependent f-numbers increased the contrast relative to both constant f-numbers. As before, the outperformance is most pronounced for a single plane wave. The common carotid artery required a constant f-number of 2 to eliminate all visible image artifacts. Again, this f-number reduced the lateral resolution. The frequency-dependent f-numbers maintained this resolution, but only the proposed f-number with a grating lobe limit of 75 degrees removed the image artifacts. So in conclusion, we derived a closed-form expression for the f-number that enforces a minimum angular distance of the first-order grating lobe. We developed a Fourier-Domain beamforming algorithm to account for the strong frequency dependence of this f-number and the associated apodization weights. Our experimental validation shows that this f-number outperforms the directivity-derived f-numbers in the removal of artifacts and achieves a similar spatial resolution as the full aperture with improved contrast. The answers to the research questions are as follows. The f-number selection should base upon the first-order grating lobes, and it is beneficial to account for the frequency dependence. Thank you very much for your attention.